Welcome back. Today, we're going to be talking about the smallest multiple uh, algorithm on Project Euler. You can see the solution's already there, so I'll go ahead and hide that. Um, so yeah, 200 or 2,520 is the smallest number that can be divided by each of the numbers between 1 and 10, and we need to find the smallest or the least common multiple for the numbers between 1 and 20. Um, so if you look here, this number does not equal simply multiplying all these together because that would be way too large. Um, so how do they do this? Well, um, if you do a factorial or a factor tree of 25 220. Let's see, you would get uh, 10 that splits up into 5, 2. That gives you 252. That is divisible by 3. That leaves you with, let's see, 252 divided by 3. Leaves you with 84. That's divisible by 3 again. So 3, that's obviously divisible by 7. Um, and then you're left with 4, uh, which is divisible by 2 twice. So what do we have here? Let's go ahead and rearrange these. 2, 2, minus 7. What do 2, 3, 5, and 7 all share? They are all the prime numbers that are in between 1 and 10. Um, Now, why are there extra 2s and extra 3s, and how do we determine that how many extras they're supposed to be in? Well, if you look, this is 2 to the third, which is 8, and this is 3 squared, which is 9. So what we actually need to do is for between 1 and 20, we're going to need to replicate this where we're going to get all of the prime numbers that are raised exponentially to a power that is still less than uh, the upper limit of this, while also being as great as possible. So it has to be the highest exponent possible for that number. It also has to be less than, or it has to be possible within the upper bound of the limit that we have. So what does that look like? Well, 2 is going to be there 4 times. 3 is still there just twice. 5, 7, 11, 13, 17, 19. That's what we need to return. Previously, we've talked about finding primes on this channel. So I don't know that we're still going to do it for this, but I don't know that I need to explain it as much as I have. If you want to do that, you just got to watch the other video that I made on finding prime numbers. But that's going to be the first thing that we're going to have to do is we're going to be finding prime numbers within this boundary. So you see, I already took the liberty of typing out, the function declaration, the first variable, and the return. So uh, what else do we need? Well, we probably need a place to store uh, the factors that we're going to be multiplying. So let's go ahead and declare that. Um, I think that might be it. So there's going to be, like I said, we're gonna need to find primes. What do we need to do after that? Well, after we do, we need to raise them to a power that is sufficient, uh, or where they're still less than the upper bound, less than or equal to the upper bound, but they need to be raised to that point. So 2 needs to be raised to the power where it is equal to 16. 3 needs to be raised to the power is equal to 9. 7 needs to be raised to the power where it's, 7, but we need to check and make sure we cannot raise these any further. What do we need to do? Well, let's go ahead and I'm going to go ahead and split this up into finding the prime first, because it's going to be its own little separate thing, and it'll be nice to just kind of have it separate. So let's go ahead and check this. We're not checking for 2. We're going to iterate through the odds. We're not going to do that long one. We're just going to keep it short. Takes about the same time anyway. Let bool prime equal true. J. Now we could have done this as a for loop. I am not doing that because we're going to have a for loop inside of this, and sometimes I just feel like it's easier to sort of like talk about which loop I'm talking about when they're different kinds of loops. So reality is, you're fine to just you're fine to do a for loop out here. For let I equal 3, I is less than upper bound, I plus 2. Let So what do we want to set this to? Set this to 3, right? Well, if we're checking for the factors, let's factors j less than or equal to square root math square root of I j plus plus, and then if factors j if I is divisible by this with a remainder of 0, then we are going to get it right once. Push I. Oh no, never mind. That's not what we want to do. We want to set full prime equals false. The opposite of what we want to do. Break. If full prime, we don't. All we're doing is checking to see if it's true, and it is, so we're fine. We can just do that. That now we're gonna push I. Full to true. And let's see, I plus equal to. All right, makes enough sense. We've done this before. Nothing's new. I don't think we need anything else outside the while loop. Should be good there. Okay. Next thing we need to do is raise the powers. Let's go ahead, since we already made this other thing a function, we'll go ahead and do this too. So for let I equal 0, if I is less than, or yeah, we need factors length I plus plus. Okay, so if it is in that, what are we going to do? Well, let's. This is going to hold while we're raising up powers. This is what's going to be holding the number as we're raising it by the next power. Another loop. I know I just said while loop, having a for loop in. Oh well. J equal. We need to make this equal to 1. Yeah, because the j is going to be the power that we're raising it to. This is the powers function in JavaScript. So the first number is the the number that you're raising. Factors I. And then the second number is the power that you're raising it to. J. Oh, wait, I need that on this side. That is less than upper bound. Then, oh, sorry. So finish this out. Plus. And temp storage equals B. Okay, and okay, so now that we've done that, once it exits this loop, we'll say factors I equal to temp storage. Okay, that should be right. So that's now raising each exponent. And then the last thing we need to do, and again, might as well make this a function since we're already doing that elsewhere. Let's multiply each of the elements of the array together. And this is where we're going to use that product declaration that we had. Factors. One. Okay, so product equals product times factors I. And since I've made these into functions, yeah, need to call them. What do I call the second one? Highest exponent. Okay, clear. Let's go ahead and console.log least common multiple. Cool. The upper bound is 20. See, is that the right answer? 232, etc., etc. Looks like it. Okay, so let's just kind of go over what we did again. We have three main components to this. We got to find prime numbers that are in between 1 and the top limit. If we were doing this differently, where 1 wasn't the bottom limit, we'd have to set this up differently. But because we are, we get a little bit of a shortcut. Once we have that, we iterate through that entire array, and raise each member element of the array to its highest power. There's a way to cut this down, frankly. If you do, instead of having it like this, you could do like factors I is less than the square root of I think this should return. We can actually see factors I. It has to be I less than math square root per bound. This should return the same result. Go ahead and see if it does. Yeah, it does. So this'll you won't be checking every number. It'll save a decent amount of time on larger. If this were 100 instead of 20, it would shave a bit of time off, and it matches the O complexity of this one up here. So added bonus, I guess. Um, and so what this is doing is it's going through checking and saying, okay, can this be raised to, a higher power? If it can, then okay, great. Let's plug that in. And if it can't, then it obviously does not do that. Um, then we call the function multiply array, and that's just going through and multiplying each of them together. Then we call each of those functions. Again, you don't have to put them into separate functions. It's just this can get kind of long. I know obviously it's not that long, but there's three separate components going on here, and it's nice to sort of break them up. Obviously, you could just as easily create a few spaces and some comments. Might accomplish the same goal for you, but I just figured since we're going over this, easier to split it up. So you can see this can probably handle a bit more. Might be infinity. Yeah, we're getting close to it. Yeah, obviously the answer is going to exponentially go up because you're adding more primes. By the time we're at 100, we're not six. It's not 2 to the fourth power. It's fifth, sixth power, and then 3 to the fourth power. Yeah, 3 to the fourth power. 5 is still the second power. 7 is the second power. And then 11, 13, etc. But yeah, hopefully you guys found this informative. As always, if you like this video, you want to see more, drop a like, maybe subscribe. You let me know in the comments if there's uh, other algorithms you want to take a look at and stuff like that. You can check out my GitHub. I got the answers for the first 10 Euler problems on there. So this is included on there. It's a bit of an older code, so it doesn't look all that neat. But it is up there as well as some other ones. Yeah, till next time.